for those who have been living under a rock, we live in an expanding universe. We know this because we look out to the universe, we see galaxies, and they're features in a spectrum that we attribute to various chemical elements. Carbon has a fingerprint revealed in a spectrum. Oxygen has a separate fingerprint. Every element has its own signature in the spectrum. So you know what the pattern of lines of features looks like on Earth. You look at the galaxy, you find that same pattern, but it's shifted. You can conclude that the galaxies that show the shift to longer wavelengths of light are moving away from us. It's what we call a cosmological redshift. It shifts because space itself is expanding. And so the wave, as it moves through space, gets stretched in the expansion, the fabric of space and time itself. And so, if everybody's moving away, turn the clock back, you can ask the question, when was it all in the same place at the same time? That was 14 billion years ago. That's how we date the Big Bang. We look around, turn the clock back. And which way is everybody going? Back to the same spot. It looks like we're at the center. But the signature of this expansion would be revealed no matter where you are. If you go to this other galaxy over here, this expanding fabric of the universe will look like it's centered on this galaxy as well. So everybody was at the center 14 billion years ago.
If you imagine a balloon, and you think about putting little dots on the balloon, and then you blow up the balloon and the dots all stay the same size, but the balloon keeps getting bigger, so the space between the dots is larger. That's really what's happening. It's not so much that galaxies are flying away from each other, but rather that the space-time between galaxies is continuously growing. This is the Planck map. This is a map of the universe when it was about 380,000 years old. Basically, this map is isotropic, it's homogeneous. The differences in color are 1 part in 10 to the 5. These are very small differences, and we're looking at temperature. So these are very small variations in temperature.
The object that can be measured with the most precision is the cosmic background radiation. When the universe was a plasma, the radiation was essentially locked to the matter. But then, at about 400,000 years, the universe cools enough so that the plasma neutralizes. It means that a typical photon that we see today in the cosmic background radiation really has been traveling on a straight line since about 400,000 years after the Big Bang, which in turn means that when we look at the cosmic background radiation, we are essentially seeing an image of what the universe looked like at 400,000 years after the Big Bang. The early universe, we believe, was uniform in its mass density to about 1 part in 100,000. But at the level of 1 part in 100,000, we actually see in the cosmic background radiation that there are non-uniformities. Small non-uniformities in the mass density are gravitationally unstable. In regions where there's a slight excess of matter, that excess of matter produces a gravitational field pulling more matter into those regions, and it forms galaxies, stars, planets, etc.
An enormous success of the Big Bang model that's not as well publicized as the microwave background is the fact that the amount of helium in the universe, remember the universe mostly hydrogen and helium, is too much to have been produced by normal processes in those 100,000 billion stars. We understand stars very well. There is not enough helium made in all those stars to make 1/4 of the mass of the universe helium. However, the entire universe, 3 minutes after the Big Bang, was the temperature of the center of the sun. And like the sun, it made helium and other light elements. It didn't do it for long because it was expanding. The sun is stable. And in fact, not only helium, but 3 other light elements have their abundances measured in space. And their abundances of 4 different light element species match a single parameter, a single quantity in the Big Bang model, which is the density of matter, that 4% slice of the cosmic pie. This is a stunning success of the Big Bang model, because otherwise you have to explain where these light elements came from, and there's no other mechanism to explain them. But the Big Bang brilliantly explains something that happened in the first few minutes.